Okay, so this is section 15.5. It's not the most important section, but it does start a discussion on surface area that ends up being super important. I've talked about flux with you guys before, and flux is all about surfaces that live in fields, like a magnetic field or a gravitational field or something like that. And when you compute flux, you're trying to find the component of the field that's perpendicular to surface area, to a surface, I should say. And when you compute flux, it's just the perpendicular component of the field times surface area. So we need to be able to quantify surface area to compute flux. And so that's really the important part of section 15.5, surface area. And we'll use some of these ideas a lot in chapter 16. And again, in chapter 16, it's almost just, okay, we're going to bring everything back you ever learned in calculus and vector calculus, but we're going to put it inside of a field. So what happens when you have a field passing through a surface? What happens when you move something through a field along a path? That's chapter 16. But for now, surface area is super important in chapter 16. Let's start now. As often begins, this often begins with a nice picture. So we're going to go ahead and do our best here. This is a region in the XY plane. So I'll be putting axes down in a second. And we'll just call that thing R. But then there's going to be a surface above it. It's going to be a little bit complicated. So I'm actually just going to start by drawing a vertical line up just a certain distance, maybe like that. And then copying my parallelogram up to that height. Like that, maybe. I'm trying to get it straight here. That's good. Okay, so that's just sort of a parallelogram, a prism, if you like, or a parallelepiped. All of those are the same thing right now in this context. And I'm going to probably pull this a little further down. I just don't want it to be too crowded in here. All right, now I'm going to have a surface kind of rising up from this. The first thing I'm going to do is a tangent plane. So I'm going to bring up some vertical lines here real quick that go up, just kind of rising up from all of this. Maybe. Okay, so those, well, actually, hang on. I'm going to erase that last one and copy this first one over. How's that going to work? One thing at a time. Okay, so let me go ahead and put my tangent plane here. This is just going to be a tangent plane to a surface that I haven't drawn yet. Okay, like that. And then I'll copy those two because this is just another parallelogram. It's sloping upward. So that's tangent to a surface. So the next thing I'm going to do is I'm going to have a surface rising that is going to look sort of tangential to all of this. So I'm going to extend these gray lines that I've drawn up just a little higher. Okay. So the surface is going to curve up to these lines. So I think I have to switch colors again. And just a little bit tricky. This is a curved surface. Okay. Yeah, close enough. Okay, so the blue is the surface. What I'm interested in is finding its area. Again, we're studying surface area right now. But we always use linear approximations when we compute hard things. So the linear approximation to a curved surface is its tangent plane. And the area of that little red tangent plane is going to be the same as that of the surface as long as you let the differentials go to 0. Okay, and so oops. Okay, so you might call this patch of surface with area delta S. Okay. And down here, the tangent plane is the linear approximation. With area ds. We have to have a delta x and a delta y, so we'll make this delta x, or dx is the same thing. And over here, we'll call that dy. And of course, the let's say ds approaches delta s, I'm sorry, as dx and dy both go to 0. Okay, so let's go ahead and of course, when we do integrals, of course, those go to 0. Let's go ahead and find a formula for ds using the linear approximation. Okay, so remember that slope is rise over run. So it's very, it's very common to use the rise as the slope times the run. Okay, so we need to quantify two rises on the tangent plane. Okay, so I don't know what color to use. Purple is going to be hideous. What about that? So, beautiful, love it. So that rise is going to be the slope. Now that's with y varying, so that'll be fy dy. I'm going to clean that up a little bit. Pardon me, everybody. Just give me a sec. I'm just going to rewrite that. Okay, so we're looking at the rise on the tangent plane only. But only allowing y to vary. So the rise is fy dy. Okay, but then if x varies, that'll be another rise. I'm going to write this. So I'm going to write the increment fx dx and then do the brackets. Like that. Maybe I'll do that in purple also, so you can see it. Okay, and then I'm going to create two vectors. Okay, so the first one, oh gosh, this is horrible. This is so hard to squeeze in. Okay, first of all, I hate that, so I'm gonna move it. So sorry. It's just horrible. So somehow I got to work this out. Wrong color though. Ooh, that's a good one. Okay. Now, I want to create my new vectors, so I'm going to have to do this with a really dark red pen. So here comes a vector. Okay. Right there, and then another vector. Remember, we can find areas with cross products. Area of a parallelogram is the magnitude of a cross product. So that's what I'm working on here. And that's a kind of an ugly parallelogram, and I need to find its area. So let's go ahead and name the vectors. So for the x displacement, let's go ahead and call that vector A. And for the y displacement down here, we'll call that vector B. Okay. And then the rest is just algebra. So the worst is over. Let's go ahead and quantify what A and B are. So A has an x component, which is just dx. There's no change in y for A, so the y component would be 0, and the z component is the rise, which is fx dx. Okay. B, same. B is going to be kind of the same, but for B, there's no motion in x, so the change in x is 0, but the change in y is dy. Of course, the change in z is fy dy. Okay, any questions? And now we're really close to figuring out what ds is. So let's come over here and just start working at ds. Now I got to back up a little bit because I realized I did a mistake. So we always use a capital S for surface area. So make sure that's a capital S in ds. I think I'm okay on the other S. These are all capitalized. Lowercase s is for arc length. It's unfortunate they use really similar symbols for arc length and surface area. I think it's just because the formulas are so similar between arc length and surface area. You always have the square root of 1 plus some squared stuff for arc length or surface area. Yeah, well, let's see here. ds, now I think we can go ahead and do d capital S would be the magnitude of A cross B. So that's just the definition of this. Well, that's one formula for the area of a parallelogram. Okay, so I think we can go ahead and set this up. Now that's a magnitude, so I'm going to do the magnitude, and then inside is a determinant, remember. Okay, and you have the ijk in the first row. Second row will have a dx 0 and fx dx. Then the third row will have a 0 dy, fy dy. And I always save the ijk for last, so I, j, and k in the first row. Okay, again, a determinant and then the magnitude. All right. So let's see here. We'll go I. Oh, we have a magnitude outside of there. And then we're going to do 0 minus, looks like an fx dy dx. Dy dx, that sounds like dA to me. Okay, and then minus j. Okay, and diagonally we're going to do fy dy dx. And then minus 0. So that's doing these here. Okay, I'll take that out. And then plus k. Oops. And so k is just going to have a dy dx. Like that. So let's go ahead and set this up as being the magnitude of the vector negative fx, negative fy, and 1. And we'll put the dy dx outside. Like that. Differentials are positive as long as you don't screw up the limits and put the lower limit as the upper limit, and then it comes out negative. But these will be positive if you do it right. So we'll say this is the magnitude of negative fx, negative fy, positive 1, and then just times dy dx outside. Those are positive. Now the rest is somewhat similar, as I say, to the arc length formula. Fx squared plus fy squared plus 1 squared is 1, and then we'll just say dy dx, which is dA. Okay. And of course, so that's ds, capital S. And so S, which is surface area, will be just a double integral of ds, okay, over some region in the xy plane. Okay. Okay, so so if S is a surface, defined by Z equals f of xy, where x, y represents all points in region R. Okay. Then S is just a double integral of ds over the surface, okay, which is a double integral over the region R in the xy plane of what ds is, and that's the square root of fx squared plus fy squared plus 1, and then of course dA. So that's the formula for surface area. It's a general surface area. It doesn't have to be I mean, you guys have done surfaces of rotation in the past, and those always involve single integrals and some clever tricks, but there's no tricks here. That'll evaluate just about any surface. We'll need to generalize this to surfaces that aren't functions of x and y, like a sphere, you know. And there's other surfaces that we'll want to be able to find areas for that aren't tidy like this. That looks great. These can be horrible, horrible integrals. Okay, so here comes an example. Okay, let me just pause. Any questions? Okie dokie. Let's do an example here. So we'll have f of xy is equal to x squared minus 2y plus 5 over 4. Who comes up with this? I don't know. X squared minus 2y, I think it says plus 5 over 4. Okay. And R is the rectangle. Here we go again with vertices. This sounds familiar. Okay, so my vertices are 0, 0, 2, 0, and 2, 4. Okay. So I guess we can draw that real quick. We'll need the equations of the curves here. Okay, so obviously I think it's y equals 2x and y equals 0 on the bottom. So that's our region that we're going to integrate over. Okay, is there any questions? I'm just going to pause for a second, let you guys catch up. Ask me questions if you come up with some. Ooh, I screwed that up. I hate it. Any questions out there?
Is that supposed to say triangle?
It is. Thank you so much. Yeah, that is not a triangle, is it? Sorry, not a rectangle. It is a triangle. Thank you so much. Anybody else? Other questions? That was a good one. All right, well, let's see if we can evaluate this thing. So fx is going to be just 2x over 4, right? So that's x is 1/2 x. Fy is just going to be -1/2. So -2 over 4, so that's -1/2. Okay. Okay, and then the surface area is the double integral over r of the square root fx squared plus fy squared plus 1 dA. Okay. And so this is double integral square root. So fx is going to be 1, I'm just going to say x over 2 on that. So x over 2 square plus -1/2 square plus 1. What's that? That'll be dA. And we can put limits on. Let's say dy dx. So y is going to go from 0 to 2x. Remember, it's curve to curve on the inner limits. Okay, these are not constants, they are curves. So y is 0 on the bottom and y is 2x on the top, and then x goes from 0 to 2. Okay, it looks like a hard integral, but it turns out nicely. You'll see. Okay, any questions? Okay, so integral 0 to 2, integral 0 to 2x. We got the square root of x squared over 4 plus a fourth plus 1 is plus 5/4. Any questions? That I don't like to integrate things like that. We can bring out the 1/4, right? How about if we call this just one more step? Integral. Let's put a half out front. So we have the integral 0 to 2, integral 0 to 2x, and it's just the square root of x squared plus 5, right? And dy dx. And then you can't, it's an ugly integral, but the good news is it's dy. This would be hard if you did dx first, because that's a hard antiderivative. You have to do that with a trig substitution, or look it up in a table. I don't want to do either one of those, but notice if you do dy first, then you just get a y in front of this. So you could say it's 1/2 integral 0 to 2, and then there would be like just a y, where y goes from 0 to 2x, times the square root of x squared plus 5, and then you get dx. So it's just 2x, and now that's actually an easy integral. And let me just leave it like that with a 2x inside. So you got the 1/2 integral 0 to 2. There's a 2x integral x squared plus 5 dx. And now you're going to say u is x squared plus 5. And du is 2x dx. And so we're flying along. You've got a 1/2 integral of just the square root of u, du. But if x is 0, then u is 5. And if x is 2, then u is 9. 5 to 9. Okay, almost done. So that's u to the 1/2. So you got this 1/2. You're going to go u to the 3/2, and you have to multiply by 2/3. And again, u to the 3/2 from 5 to 9. So that's 1/3. And you're going to have 9 to the 3/2 minus 5 to the 3/2. And 3/2 is 1.5, so you could do 9 to the 1.5. So that's 9 times 3. 9 to the 1 plus 9, or times 9 to the half. 9 times 3. I think that's 27. So you have 1/3 times 27. 5 to the 1.5 is 5 to the 1. It's 5 to the half. So this is minus 5. 5. Like that. So I think that's 9 minus 5/3 root 5. Okay. So that's the surface area. And these problems have to be cleverly designed, because generally they're just really hard problems. And the homework problems are just absolute works of art sometimes. I wouldn't call that one a work of art. But it was doable. We were able to solve it, and that's not normal. Okay, what time is it? 8:19. Let's try and squeeze one more in. This one's hard. I call that last one easy. Okay, this one's hard. Here it comes. Find the surface area. Find the area of the surface on the sphere x squared plus y squared plus z squared equals 4. Okay. So that's a sphere of radius 2. Okay. That lies above the plane z equals 1. Fascinating. So I'm going to have to figure out, that's not going to be the whole sphere. You got that on the first try. That's nice. I don't like some of this. I'm going to move my x-axis a little bit. Pardon me. Doesn't look right. That's better. That's good. Okay, now I have to do sort of an oval up above. So, I'm going to try and do an oval up here. That didn't work. Try harder is what they say. What I really, yeah, that's good. That's fine. I'm going to squish it a little. It's good. So I'm not going to try and draw the whole plane, but this disk that I'm drawing is part of that plane. Yeah, so that's just a flat disk there where z is 1. Okay, and then the surface I want is above that. So now I'm going to color that in red. Okay, so maybe I'll just call it S up there. Okay, any questions? Well, I need to know the radius of that circle because I'm going to move this into polar coordinates. Okay, but I don't know this. I know that the sphere has a radius of 2, I think. So this is 2, this is 2. But what's the radius of the circle? We'll figure that out. So that circle right there is the intersection of the plane and the sphere. So let's do it's always the if there's 2 surfaces, you're always kind of thinking, well, what's the intersection? So let's talk about the intersection. So you're just gonna make z1. So you got x squared plus y squared plus 1 squared equals 4. So that's easy, right? So x squared plus y squared equals 3. So that's radius square root of 3. So that'll be good to know. Okay. We're going to be integrating over a circle whose radius is the square root of 3. Okay, now we're going to get some partial derivatives set up. So let's go ahead. We have to write this as a function of x and y. So going back to the original surface, x squared plus y squared plus z squared equals 4. I'm sure there's a better way to do this, but based on what we're working with right now, we need to know z as a function of x and y. Don't I just plug in z equals 1? I did. But on the surface, Bilal, so on the surface, z is bigger than 1. You follow me? That z equals 1 is just what cuts the surface off, but the surface lives above that. Okay, going on. So you're going to have z squared is 4 minus x squared minus y squared. So z, we only want the positive, so it starts as a plus or minus. But then we're going to go positive. Okay. And now let's take derivatives. So this is our f of xy. Okay, so fx is going to have a negative 2x over 2 square roots. That's the negative 2x is the derivative of the inside. And the derivative of the square root is 1 over 2 square roots of. So this is just negative x over the square root. And it's just logical that fy would be sort of symmetrically the same, but have a negative y on top. Okay, so those are the two partial derivatives. And then don't forget, you have to do the square root of 1 plus fx squared plus fy squared. So let's do this now. The square root of 1 plus fx squared plus fy squared. Did I make it clear why we're doing that? So going back to the formula up at the top. I guess it's fx squared plus fy squared plus 1. Same thing, right? So, you know, if you're going to be uptight about it, then you could write it like that, just because it makes people feel better. Okay, so here goes. I'll do the square root in a sec. So you're going to have an x squared over 4 minus x squared minus y squared plus y squared over 4 minus x squared minus y squared. And then plus 1, which is going to look like 4 minus x squared minus y squared over 4 minus x squared minus y squared. And that's all inside of a big square root. And so the x squares and y squares cancel. So you just have 4 over 4 minus x squared minus y squared. All of that in a big square root. And why not just say that that's 2 over square root of 4 minus x squared minus y squared. So there you go. So the surface area, now I want to draw this region that we're integrating over. It's a circle. Okay. So this is the region in the xy plane. This is a circle whose radius is the square root of 3. And I colored that in blue before, so I'll do that again. Okay, so that's the region you're integrating over. This is the projection of the surface into the xy plane. I'll just say of S into plane. And that's always what you integrate over. You don't integrate over the whole sphere, just the projection of the thing you're trying to evaluate. So S is that surface, but you have to bring it down into the plane to integrate over it. Okay, so here goes. Surface area is double integral over r of square root of fx squared plus fy squared plus 1 dA. So this is going to be like this. 2 over square root of 4 minus x squared. I'm going to do that as a minus and then parentheses x squared plus y squared, like that. And then a dA. And we're going straight into polar. Okay, so that's r squared. X squared plus y squared is r squared. dA, remember, is r dr d theta in polar. So this is a double integral of 2 over square root of 4 minus r squared. dA, which is r dr d theta. R, remember, you're not integrating over the whole sphere or hemisphere, you're integrating over a circle whose radius is the square root of 3. So if I draw that little kind of that patch here in polar on this thing, my little patch is just part of one of these slices like that. Okay, okay. And at the tip of the patch, r is 0. And on the outside edge, r is the square root of 3. And those are your limits on r from 0 to the square root of 3. Okay. Theta, you have to go all the way around. Remember, theta measures up from the x-axis. So just real quick, I'll draw theta here. And theta, you have to do the whole circle. So theta is going to go from 0 to 2 pi. So 0 to this, let's pound this out. We got 1 minute. 0 to the square root of 3 and 0 to 2 pi. Okay, your u is going to be 4 minus r squared. And du is going to be negative 2r dr. So there's an r dr. That works out nicely. Negative 1/2 du is going to be r dr. That works. Okay. So I'm going to have a negative 1/2 out front. It's negative, so the limits are going to get turned backwards real quickly. 0 to pi. I'll put limits on in a second, but they'll be backwards because the differential is negative. I just have 2 over the square root of u, which is going to be 2u to the 1/2. r dr is the negative 1/2 du, and then there will be a d theta. So when r is 0, u is 4 minus 0 squared, so the lower limit on u is 4. That's a u to the negative 1/2, everybody. When r is the square root of 3, u is 4 minus the square root of 3 squared, which is 4 minus 3, that's 1. See how the limits are backwards? And that's because the differential was negative. So I might square that up and say, well, that's 1/2 integral from 0 to 2 pi, integral from 1 to 4 on 2, oops. Probably just get rid of the 2, right? And the 1/2. So let's get rid of that also. So you'll just have u to the negative 1/2. And then the du d theta. And now we can go very quickly. Okay, so u to the 1/2, you add 1, you get u to the positive 1/2 times 2. So there will be a 2 integral 0 to 2 pi. It'll just be u to the 1/2, which is the square root of u, where u goes from 1 to 4. I fixed my upper limit up there, so it goes from 1 to 4, and that'll be d theta. So I think, does it get much easier than this? Square root of 4 is 2, minus square root of 1, that's 1. So that's d theta, 2 minus 1 d theta. I think, and that's from 0 to 2 pi, so I think you're just going to get 2 times 2 pi, right? Which is 4 pi. Double checking. That's what I got in my notes, so it's good to go. All right, guys, class is over. Sorry to go over by 3 minutes. And have a great day. I've got an office hour on Friday. If you need to talk to me, send me an email. If you need to upload your homework again because you forgot a cover page, please do that. There won't be any penalty. I just want that cover page on there. Make sure it's filled out. Put in the number of problems you did for each lesson, and then re-upload your homework, and I'll be happy to give you credit for that. Okay, see you guys.